Asynchronously answer a question. All right. So you're the only one here, so go ahead and
Find the pressures on each of the faces of the WaveWriter using the UT calculator. So
oh yeah.
we got a 3D object.
Yeah. But the trick with the WaveWriter. So forward. We've got the in 2D, we've got basically a wedge, which creates a shock. One. And the BT calculator, this is just an oblique shock. So up here it's shock 5, and no other conditions. So post shock, what happens? You got a streamline that comes in, it's bent to match this, right? Get that out of the calculator. Actually, you put in the data, you get the beta. But this streamline same that. And then you also, from that calculator, get all of the M1 to M2, P1 to P2, all of those relations. So if you know the pressure here, use the shock chunk calculator to find pressure here. P2. And then that's the pressure that's pushing on the bottom surface of your WaveWriter. It doesn't matter that it's actually D, it actually tucks down to this. Back here. Look. This is all P2. I think this is all P1. P1 is pushing down on the entire upper surface. P2 is pushing. So that's, I mean, that's the beauty of the simple shape. It's just ridiculously easy to solve for.
And when we do those alpha deflections, you're still going to have a constant
So
pressure.
you don't need, so I kind of wave off of using the impact method and the calculator, or you could do it on the other mock cases if you want. Those are easy. But for the well, the other mock cases won't be exactly right because the shock is no longer planar. Right? It bows out or goes in a little bit depending on the mock number, and that means the condition here is no longer quite a constant. Close, but not exactly.
I see.
Actually, I'm trying to. Well, yeah. So it'll become slightly 3D. It should be. The disturbance isn't very severe, so probably in the off mock cases, you'll get pretty close to the right left. And the other cases, it gets harder. What you really need is you need to find, especially for the impact method, you need to find the angle between the incident flow and the surface. But it's a kind of tricky geometry. You can't just say, oh, it's whatever theta I had before plus the alpha, because it's at kind of a weird angle. So that's where, if you actually want to find that, go back to SolidWorks. Use SolidWorks in order to draw the vectors, like what you want is the normal to the lower surface, the free stream, find that angle, and then the deflection angle is pi over 2 minus that angle. So it's, and yeah, boy, you can go through the exercise if you want. The trouble is impact theory is not that great to start with. So you add in additional uncertainties.
Okay.
Kind of, but that's in general, that's if you had like a super arbitrary shape, some crazy shape. Usually you would define this by having all these like little triangular segments that encapsulate the surface. And then on any two of these lines, you could do a cross product, which gives you a vector that's orthogonal to both of them. And then you take the free stream and find the angle between that vector and free stream. So there's a mathematical procedure to solve it for any arbitrary shape. But anyway, it's the same technique you would apply here. But anyway, I think what you'll find is that impact area, at least at the lower Mach numbers here, like 5, it's not super awesome. Again, a little for first order kind of thing.
That's only because as we get to higher Mach numbers, it's.
Yeah, that
closer.
gap gets closer and closer and closer. You'll find that. And the other defect we have here, which not really a problem on the on-design case, because the upper surface is free stream. But when you crank the angle of attack down, they've got an expansion on the top. And impact theory ignores that.
Mhm.
But as the Mach number gets higher and higher, ignoring it turns out to be less and less of an error. Yeah.
Thank you.
Okay. Hey, guys. You guys online have any questions?
I do have a question for, can you hear me?
Yeah.
I do have a question, for homework 6 regarding the U infinity and V infinity.
Yeah.
I moved the equations from the R gas and the gamma and just put the values. And then it's telling me that the units have now a Kelvin in it, which it doesn't make any sense. I'm trying to go through all the units again. But for somehow the U and V has Kelvin in it.
So I'm guessing in the definition for R gas, was that joules per kilogram per K?
Yeah,
And your T infinity was also K?
okay, yep,
Ah,
should cancel out, right?
they should, yes. I don't know where else you could get a K in there. Yeah,
I don't have any other case.
How do we, for the unit joules per kilogram Kelvin, how do we write it?
yeah. How did you, I mean, write on the board the way I would do it? Well, the easy way I would do it is usually joules per kilogram per K, but that has to be a capital K. What it technically means this. So you want to make sure the K is in the denominator, not in the numerator for gas.
Okay, I did joule divided by kilogram multiplied by Kelvin, so probably
Yeah,
it
so
doesn't
without the
repeat them.
parentheses, the divide kind of does that, and so that's like the shorthand, but mathematically ambiguous way to write it.
I
That's
see.
what
Okay.
I think that's the way I did it in the notes. Yeah, that would do it, because then you'd have a square value of K, which would end up in the speed of sound, which is a square root.
Oh, I see.
Yeah,
I'll try through one.
their tool for tracking the units is pretty useful for debugging typos that I do in my expressions. Did you get it?
So I got the files. I didn't get a chance
To look at them?
to look at them, but did you actually like cut them the way?
I did. I mean, there's a million ways to cut it. I think I cut it differently. That's it's in the gouge, but
Okay.
it ends up with the same thing. We can go over it if you want.
Yeah, I don't have SolidWorks.
I can bring it up here and we can just do it if you want.
Sure. Yeah. Like I just I think I either misunderstood it or didn't like understand the language in the.
Yeah.
Just like it sounds like, in the original outside header domain didn't get like divided properly.
So both of them look like exact copies of the original huge
Yeah.
block minus the chunk of the WaveWriter.
Because I think SolidWorks, anytime you change one relation, it like asks if you want to save it and close it, or like there's
Oh,
like 3 different options about how to proceed once you
yeah.
save a
Oh, so you think you were maybe working in that's possible.
possible. Like yeah,
Yeah, a lot of times I mistakenly forget to tell it to save as new and and then I end up editing the original, which I didn't really want to do.
yeah,
And yeah, so that's it's easy to do that.
yeah. I guess for future reference, it might be helpful. We could probably do some. Wow.
Yeah, yeah,
Yeah, I guess you don't mind.
yeah, sure. Yeah, we can do it. Let me let's see. Share screen. And let's see. Find your files. Yesterday. Here. Yeah, 5. So here's inner and outer. So let's just one. It's complaining because I already have an inner and outer. I'd be open to files of the same name. So that's what you labeled as inner, and all it has is the original block plus the cavity. So if you did other edits, they're probably in. So I can try to find them. They're probably in the other. Would be in fluid domain, maybe. No, it's still only something. I don't know. Somehow they didn't say it.
Well, there's one more that has the waiver.
I think that's wasn't there assembly?
Yeah, that would be,
I didn't. Guess I didn't open the assembly.
yeah.
Oh, the trouble is the assembly. It's kind of like a project file for ANSYS. There's no data in it. It uses says you can use the reference files, and we've looked at the reference files.
Well, it also includes the waiver, right? It's just fluid domain.
Yeah, right. Oh, I did look at it at home. Yeah, and it looked like it was. Let's see. Yeah. Oh, it's not finding a component.
Yeah.
Oh, because I didn't download it. Okay. Okay, let's get point about it. Yeah. Okay. So you got that assembly. You got the cavity made. It was just the cutaways to make an inner and outer.
Yeah.
That's all that was
That's it.
missing.
Yeah.
Do you want to just go through that real quick?
Well, yeah. We just need the horizontal.
Yeah. So this was that's fluid domain inner. So, like I said, there's SolidWorks was always an infinite number of ways to do the same thing. I think the quickest way is the one I actually did last night. It's the quickest way I figured it out. So first thing to do is make it transparent because we need to access that line. This is the inner, so we want to cut away everything except that inner bit. So I'm going to cut on this. This is the symmetry plane. I'm just gonna sketch all this stuff I want to get rid of. It's, you notice it's snapping to all the corners.
Yeah.
One right there.
Maybe it's.
Okay. Yeah, I think other times I do it from the top. I think this is actually the quickest though.
Well, no, it showed this, like this view, it just like
Okay.
select the bottom line and then.
Oh, so instead of clicking on the points, instead you can highlight these, like I can highlight this and then do a convert.
Right,
But yeah,
that's what it said.
uh,
Didn't really-
yeah, and if you don't look at this thing head on, you can't click on any of these points. Well, the ones on the front face you could because they're on the sketch plane, but I couldn't reference.
Yeah.
Sometimes you can't reference things that are behind. Yeah, and then when it cuts, it's gonna actually leave two chunks of fluid. But I only want this one. I don't want that one.
Yeah.
So this one. And so the gold one I think is the one it gets rid of.
Okay.
Yeah, so there's the inner, and then the outer is actually a little bit easier. You would select this triangle here and have it cut instead of through all, you would cut to this face.
Okay.
And it'll just rip out that chunk. When you do these nice even cut extrudes, you're guaranteeing that this interface here is actually a plane. And so the merging, when you put it back together as a assembly and load it into ANSYS, it'll recognize that they're coincident. If you were to do lofted things there, sometimes it doesn't work because even though it is actually should be a plane, the loft doesn't necessarily guarantee that it is. So like this this surface here looks like a plane, should be, but it might not be exactly a plane. Anyway, does that help?
Yes, I'm hoping I can remember that. So you, like,
You can actually see if you look in the files I sent you,
yeah,
you'll see this. And so then you can actually see the sketch that I used for it. And you can see the definition that I used for how far to cut. The only thing that won't be totally obvious, I mean, I guess it'll open this up again, so you'll see which one I selected.
okay. Yeah, thanks. Like, I'm just kind of struggling with like.
Yeah, I know. SOLIDWORKS, it's a new tool.
Yeah.
It's like one more thing to learn.
Yeah, I also, sorry, I don't know if I'm in the other. Okay, so like minor perturbation here. I don't.
On this, it's on this problem we use Newton's impact theory.
Okay.
And it's similar.
I just like practically speaking, like I'm not sure how to apply it.
Yeah.
There's the fine.
We actually went through and sort of derived it. We end up getting what CP is. It's 2 theta over beta. Or just where theta is whatever angle you bent away from free stream.
Right.
Guys online, stop sharing. One. Yeah. And then beta is the square root, box square fence one. And then this, as with perturbation theory in chapter 5 or in the homework 5, this is always free stream mock. Don't know anything about local mocks. And this is always with reference to free stream. Doesn't know anything about body parts ahead of you and behind you. And then the one major difference between impact theory and perturbation theory is that in supersonic perturbation theory, if you had an expansion surface, it would count as a negative angle here. But in impact theory, the idea is the Mach number is so high that you don't expand. Instead, you get essentially stalled flow, and it's you always assume that CP is 0, meaning that it's free stream pressure at that spot. So if we actually in here, we don't really have it. We have free stream up here. We've got oblique shock flow down here. If we actually had the back here, you would assume for impact theory, which isn't exactly right, but it's a low order method anyway, and that's closer than any other tool we got for that order.
So curious if data was
Square root.
That data.
Oh, yeah. Anytime it's a raw degree, make sure it's radians.
okay, so you calculate that for the entire.
Yeah, you really only have two surfaces. You've got the top surface and you've got the lower surface. And the lower surface we defined in SolidWorks with OS 22 degrees or whatever.
Right.
And that's the theta converted radians. Yeah. It's we were just talking about it. It's kind of a low order scheme. Probably 0th order is the right way to discuss it. I think it becomes better when the Mach number gets high. So you get up around Mach 20, 25, it progressively gets better and better. For Mach 5, it's very ballparky. About as good as perturbation theory was in homework 5. About as good as the perturbation theory was in homework 5.
Okay.
It wasn't spectacular. But you'll find the Virginia Tech calculator is exact. It's exact. And we're also talking about this. For the off design cases, for the plus minus half a Mach, you can still use Virginia Tech theory, super easy, and you can use this super easy if you want. They won't be exact because the shock it's no longer planar, it's slightly warped. So it's technically 3D flow in here, but I think it's subtle enough that it'll still be pretty good. But once we do the plus minus 5 degrees, now figuring out the angle, the theta gets a little bit hard. There's two angles involved, so
Okay.
I would say don't worry about it. If you want to, you have to go back to, I think the easiest way to do it is go back to SolidWorks, draw a bunch of vectors, measure angles.
Yeah.
It's hard. And especially for this, it's a lower order scheme that I don't see any added value.
Do you expect to like change the attitude of the wing for the slab?
The wave rider?
Yeah.
Yeah. See, it's the same geometry.
Yeah.
You'll just change the boundary conditions and CFX and rerun it.
Okay.
So the Mach number, you don't have to do anything except change the Mach number. And then the angles of attack, you'll have to change the boundary conditions, right? This will be inlet for positive angle attack. These will be inlets for negative angle of attack. Outlets.
Okay.
Otherwise, it's problem's the same. Convergence is fast. It's 100 iterations.
Maybe didn't break down far enough.
Yeah, okay. Yeah. The only time that it's perfect is the on design case because it's technically a point design aircraft. But the kind of the beauty of having the cut here with the inflation layer is that we make the inflation layer thick enough so that when the shock moves around, it's still inside the inflation layer. The plus and minus half a Mach, plus or minus half a degree is about as far as you can go. The inflation layer still stay in there.
Okay, thanks. Yeah, I guess you can still kind of respond to email during the week.
I will. I don't know if I'll have an access to like open up files and look at them.
Yeah. I don't expect. Like,
Yeah. Might be. It'll be East Coast evenings, so early for you.
We're not using the Mikado's modifier.
Oh yeah, you can do that too. The difference is that the two becomes,
The same.
yeah, you can plug your Mach number into that long equation. And so it'll be something up around 1.8,
Okay.
Um,
Depending on.
depending on the Mach number, yeah. Yeah, it's such a subtle difference. And to be honest, I can't remember, I think maybe this might be closer
So
to truth. Than
Really?
I think the modified becomes perfect at infinite Mach.
I always thought going faster made things complicated.
Yeah, no, it turns out supersonic flow is easier. Yeah, especially if everything's angular, then you can walk through designs with the BT calculator and find exact solutions for almost everything. If everything's curved, it's harder. But I think convergence, when you compare this to homework 3, this converges, and granted, it's essentially inviscid flow. But I think if you went back to homework 3, the incompressible flow, and ran homework 3 with a pre-slip boundary condition, I'm pretty sure it would still take a lot longer for this to converge. The supersonic flow, everything starts from a very defined place and travels to a very defined place. And as long as it doesn't go unstable and blow up, then everything's good. Stability ends up being the fight most of the time.
I wanted to ask if my domain was working right. It seems ran out of battery, but in the pictures that you had in your handout, I think along the leading edge, you could
Yeah, there is some noise.
there's some noise.
Yeah,
I was getting.
you have to look pretty close. And I think on one surface it's obvious, and the other surface it's not. See if I still have it up. Might. This is the. Oh, maybe it is still there. Let's see. Oh, no, that's the other. I think I have 2 of the canard problems open. Let me find it real quick.
And that noise was at 0 and all the time.
You'll find it in all of them.
And all.
Yeah. The problem is the way it tries to figure out what it doesn't really know what a sharp the leading edge is. Doesn't know that the shock should be an oblique shock attached to it. It actually tries to find like a normal to the surface. And if you look at the crazy triangular mesh when you get up there, if you tried to find a normal literally out of the leading edge line, it would be like all over the place at every point, because it's doing a numerical analysis. It's basically taking the slope of the 2 faces near it and saying, oh, the normal is halfway between those 2. But those 2 faces are like changing shape everywhere. So the normal is all over the place. It doesn't, when I was doing this for my thesis, we had our own, it was a NASA code that we were dealing with. But I had the source code. And so I literally went in and built my own sharp leading edge boundary condition where it would absolutely enforce sharp behavior. The flow going under one surface was one way, but no way to do that in CFX. And to be honest, I mean, anything viscous, you wouldn't worry about this anyway. It's only the fact that we're trying to treat it as inviscid and sharp. Let's see. I think this is the on design case. Hopefully this is not the one that blew up. Let's see. The ISO surface. Streamline. We want to look at the lower surface. Yeah. So here's the lower surface. So that's kind of typical. So it's sort of a weird split of stuff. Some of it is Gibbs phenomenon, and some of it's because the mesh is just a mess close to there. We try to do the inflation layer, but when the inflation layer gets close to the surface, it breaks down. So a lot of this is because the mesh is just horrible, close by. You could probably do better if you were to go in the inner block and you made really small cells and maybe even refine the leading edge size smaller. You could probably compress this to a smaller and smaller gap. Part of it might be, let's see, I'm using local. If I go to global, oh, right. Yeah, it's more subtle. Just because there's so many big extremes where we're like buried in this little tiny pocket here. So if you go to local, it always amplifies it. I'll actually use that on purpose a lot, especially if you're trying to find problem points. You know your solution's blowing up. It's hard to find them sometimes, but you go to local, so be sure to find that. It's looking at just the pressure variation on this surface, and it's making the min and max of this thing. So someplace there's a super hot spot. Yeah, here's all these little ripples. So this looks like almost the extremes here. Someplace there's something a little bluer. But it's actually not horrible. The exact solution's someplace in here. So we're not getting too much above it. And I think the lowest one's probably up here someplace. Yeah.
I'll have to take a quick look when
Yeah.
I am having the mesh on top. Do you think because of the flush mesh cells along the edge? That fluctuation.
Oh, on the, see what we have on the top. That yeah. Let's see. Still a pretty broad range. Oh yeah, so these are probably trying to get closer to stagnation. Now they're nowhere near stagnation, but they're definitely higher. Again, it's because of this inability to define something that's perfectly sharp. All, if you looked at the individual mesh here and kind of figure out the way it's trying to find surface normals. So probably be cases where the cell on the top and the bottom have about the same size, so the normal is pointing almost straight out. If you have a huge cell on one side and a short cell on the other side, then the normal is going to be more actually normal to the top to the bottom surface. So, yeah, and I just don't know. There's no easy way to get around that, other than you can try to make it cover a smaller region. You usually, when you make it cover a smaller region, the two extremes get more extreme. So it can actually become a problem if you really go crazy making tiny cells along the leading edge and the nose. Sometimes that can make the solution want to blow up. So it's finding a sweet spot there. But on the lower surface, you have the ability that you were to just vastly increase. You can do like a body sizing in here. And if you cut that down by an order of magnitude, then you'll probably compress this stuff to like a tenth of how far it reaches. But I think if you do the average pressures here, these oscillations, they're kind of oscillating almost about the mean, so they don't corrupt the average too much. So the average pressure is actually, I think, pretty darn close to the VT calculation. VT should be, like I said, it should be exact for It's-
I did send my first iteration when I couldn't figure out how to get the, he told me I have to deselect a couple places, like, they changed the variables that I was looking at. This was earlier last one.
Yeah, I'm trying to remember now.
I was just getting some weird.
Oh, yeah, you were, what it was, we were looking at it from back here.
Yeah,
And I thought we were looking at something on this that didn't make any sense. And this was actually transparent.
Mhm.
And oh, it's angle like this. So the bottom face was colorized. It was like red,
yeah,
and we were seeing it here.
okay.
Yeah, it was so confusing.
But
Oh, then I was trying to figure out how do we get pressure that's like white and red. Shouldn't be white at all. It should have been the giveaway.
all right,
Yeah.
I'll go take a look at my, on the, in Watkins. If I don't see that fluctuation on the leading edge,
If you don't see anything, I'll be really surprised.
Oh.
I think on yeah, on anything except absolute temperature. CMS. Total temperature, I don't know. Should be a constant. I don't know if that's there's constants and there's constants, I suppose. Yeah, so there's a little bit of noise. Should be it's tiny. It's that fourth decimal point. It's the only one that doesn't change. Else should be pretty messy. But like I said, if you go back to global, it looks pretty subtle. For sure,
it should definitely be.
yeah, it's pretty clean.
I also have my CL and CD for angles of attack of 0, 1, and 2. Did I run this right?
I don't know if I remember.
That's
Do I have the expressions in here? This one doesn't. But the math is, say, trivial.
Mhm.
I think in the gouge sheet, do I show any of them? I don't remember. I think the expressions are in the gouge sheet. I think I was lazy when I did this. Didn't throw them in. But I mean, the math is ridiculously.
Mhm.
So this is the area, right? When you're trying to get lift, it's just the vertical projection. So it's just that triangle times whatever pressure is mean on the bottom. You can actually, you can do it in the calculator. You can do it right here directly. Force, lower surface, y direction. There's our force. And then you just have to, that's the lift for the half body. And so you just have to turn it into coefficient. Like I said, I would do it inside here because it's so easy. But we already have gamma, P infinity, Mach infinity. Yeah.
You got everything I need.
Okay.
Help with.
All right. Yeah, good.
I appreciate that, Professor.
Yeah, sure. You bet. Hey guys, any of you guys online have any questions?
I'm just running the simulation right now, and I noticed something. My graph is much less steeper than the actual PDF graph, so I'm not sure if that's a good or a bad thing.
Wait, what's that?
The graph for the simulation, the momentum and the mass, it's less steeper
Oh,
than the actual.
yeah, so those don't always show up the same. They'll be dependent a lot on your mesh. So if your mesh has fewer points, they'll probably be steeper.
I have 303,000 knots. So it's probably the same knots at the example.
Yeah, I think,
Um,
I don't remember. I think, didn't the example have like 320,000, something like that? Oh, yeah.
oh, okay.
Uh, it seems like they changed the mesher. All my meshes are coming out smaller now than they used to. So I don't know if that's good or bad, but so anyway, I wouldn't expect the RMS to look exactly the same. They should look similar, just because they're so mesh specific. But the usually, I guess on that one, I don't show a whole lot. The things that you should absolutely see, to bring it back up, you should see constant pressure essentially on the top surface, constant pressure on the bottom surface, except for some noise near the leading edge. And then you should also see, flip around here and highlight some other stuff. Turn on the symmetry plane and the outlet. And on those, what are we showing? Outlet, we got Mach number. So what we would like to see for the on design case, we'd like to see this color bar to be pretty darn close to this split line. This split is the exact location of the shock. That's why we cut it there. And this color bar is basically where the shock is located. So we'd like that to be pretty much there for the on design case. And then when you start changing the angle of attack and the Mach number, you'll see that it moves. And hopefully this inflation layer is big enough so that even then the plus minus Mach, half a Mach and plus minus 5 degrees, it should be reaching just the kind of the extremes of this, but still contained inside. Does that make sense?
Yes. I'll check that with the simulation, and then after that, I'm gonna run another simulation with a different Mach number and different angle of attack, and see how that's gonna work.
Okay. The what the gouge requests is that you do 0 angle of attack at Mach 5 and then plus minus half a Mach, but still at 0. So if you do that, you can leave all the boundary conditions the same. You just change the Mach number and the expressions. And then at Mach 5, you're also supposed to do plus and minus 5 degrees angle of attack. And for those, you'll have to actually change the inlets and outlets, right, to reflect the angle of attack.
Yep.
Okay. Yeah. And they hopefully they converge about the same as the 0 degree case. Usually 100, 150 iterations is enough to be done.
Okay, and for the hand-in homework, you also need all the cases, like plus or minus 5 degrees, and also the change of the Mach number.
Right.
Okay.
And then what we were just talking about with the student in the classroom here, you can, I don't have them in these expressions, but if you go ahead and compute the lift and the drag force, and then do the lift and drag coefficients here, you'll want to export those, and you have to make some plots in Excel or MATLAB or something where you look at the change of lift and drag coefficients as a function of angle of attack and Mach. So that's basically just saving values that you get out of here in discrete values, plugging them into a plot.
How do you extract the data from here?
Well, you would get the number like I just did with the function calculator. This is getting you the actual lift force. But if I'd actually put in the expression for turning the force into a coefficient, you'd get the coefficient value. So you literally just cut and paste this into Excel. But there'll be, like I said, one of these numbers for each of the 5 cases. One for lift, one for drag.
Okay, I'll see what I can do.
Yeah. Yeah, that part's, I would say, should be super straightforward, just a matter of recording what the values are in each one of the cases. If I were you, I would save all the cases in case you have to go back The tendency sometimes is for people to see what they want here, write down some stuff, make some screenshots, and then they go into pre and they edit the settings and keep running. But that means you've basically flushed the old solution. It's no longer available to you. What I think is the smarter approach is to go in here, once you have everything you want with the solution, save it, and then do a save as next to it. Do a save as, make this the new case. So instead of Mach 5 0-degree angle of attack, I would do say plus or minus 5 degrees. And then I still have the old solution. So if I've got to go back and get something that I missed the first time around, or have to converge it further, or check some boundary, whatever, anything that you think might not be right when you're doing the write up, you'll still have those solutions to go back to. It takes up more disk space, but you have everything. By the time you're done, you have all the different solutions.
And the comparison for all the 5 cases, right?
Yeah, right.
Okay.
And somebody had a question asynchronously regarding the other, this problem. They were asking how I did the streamlines, and probably in here. So I'll just show it real quick. Sometimes it takes a little bit of hunting, and where you put the seed lines for subsonic and supersonic might not be the same, or more appropriately, they may not work out the way you would like the same. But if you look carefully, the line is just a short distance directly above the leading edge. I think we get a top view here. I think it's right on top. Yeah. Doesn't have to be on top, could be just nearby. But I think that worked okay for this one. And then what you'll find the right streamlines, probably these. Sometimes, because this is the subsonic case, sometimes the streamlines, if this line is too close to the surface, the streamlines might actually drive into the surface, or maybe they'll actually get sucked from the bottom side around and do something weird. So when that happens, what I'll do is usually just raise and lower this a little bit away from the height I've got now on the surface. Anyway, that's pretty much the only technique I know of. On some of these, I don't know if I have it on this one. Some of them I think I'd actually do the roof line instead of that might be line 3. There it is. Line 3, I did a line above the roof line. So you have to put a little thought into either go back to SolidWorks and check some dimensions, or do a little bit of thought on the geometry here. It's half of root chord here and headed toward the tip. So the geometry is not horrible, but you have to do a little bit of math. And then I think I used that for seating streamline 4, I think. What I was looking for there, the reason I did the rooftop was because I wanted to make sure I seated streamlines that were kind of underneath this vortex. So they actually get swept around over the top of it up front and then follow the surface at the back. Anyway, lots of different things. Sometimes you just have to play around. Sorry, with how you where you put in the seeds. Like I said, I think it's different for subsonic and supersonic. I think I have that one up too here, maybe. Yeah. Let's see. Line 2. They're both there, and you can see there's different heights. So I think I was moving the lower one away because it was somehow taking points and sucking them around the top surface. I think I moved it away enough to prevent that. I'll tell you, if you put one of these lines in so that streamlines drive into the surface, the computation time for integrating the streamlines becomes really big. It's a good way to know you probably did something not quite right or not desirable. The further they are away from the surface, usually the quicker the streamline integration is. Some,
My glasses case, but
oh,
not here. It's all right.
okay.
Thank you.
Any other questions?
Not for this homework.
Okay. That was all we're going to do today was answer questions. So no one's got anything else. See, Andrew, did you want to talk about homework 4 at all, or?
Yeah, I'm just waiting for everyone here to like finish the question.
All right. So, not quite sure what your level of understanding is for how this kind of solution occurs. The gist of it is that you have some number of equations that are all coupled. So, usually you would find this kind of problem with, say, like a spring mass problem, or,
Okay.
I'm sorry?
Yes, I
Okay.
can hear you.
Okay. So, usually what you've got is our W's. Here's our unknowns, gamma 1. And equal to right-hand side. So these are both n by n vectors. And I'm sorry, n by 1 vectors. And this is an n by n matrix. And do you know how to get back and forth between the n equations in this matrix form? I think maybe that's where the confusion came in. For the
I
4x4
believe
case,
so, yeah.
the W11, Q1, 3-1, 4-1, and then down to W4. And the way the equation works is you get W11 times gamma 1 plus W21 times gamma 2 plus, I think I might have the indexing wrong. I think it's MN, isn't it? 1, 2, 1, 3, 1, 4. Three plus 3, 4 times gamma 4 equals the right hand side 1. So that's one equation, right? That's the first row. That row times this vector equals the first item up here. So this is what we're actually doing. We have one equation here and 4 unknowns, which is unsolvable, right? But
Yeah.
here I've got 4 rows, so together I get these 4. I can't solve them individually. But if I put them into this form, I mean, I guess you can't solve them individually. You could manually do just a ton of manipulation here, which is fine. And with a 2x2 system, that's typically what we would do. But when you get into higher numbers of elements, the matrix solution is definitely easier, in particular because these all become numbers in here. Just, you know, you solve all the math from the geometry of your problem, these become hard numbers. And so MATLAB is just exceptionally good at figuring out how to invert that, solve for the system. And so the vector equation, usually this would be bold-base, I guess, for matrix times gamma vector equals right-hand side vector. And the solution is that we multiply both sides by omega inverse. These cancel each other out, become the identity matrix. We're left with gamma equals omega inverse times the right-hand side vector. And so this is like just one call. You can literally say inverse W, and MATLAB will do that, or I think they do a backslash operator. You could do like a backslash or a linsolve. You do linsolve for omega and right hand side. We'll do it. There's a bunch of different ways, but that's really the nature of the problem. So almost all numerics of PDEs, every one of them ends up with some huge matrix here that you've got to invert to solve for the unknowns. So CFX is doing the same. These would be like U's and V's and W's and rho's and pressures. Just imagine that it's massive millions of, it's a vector of like a couple million. So you do an inversion there, solve for the or solve for the unknowns here.
I was trying to do that in the code, but I think I did a
looked like what you
mistake
did
when I tried like
it looked like what you did is you got rid of these, tried to sum up these, and then do like somehow a divide over here. Like took the sum of this divided by this and thought it was, but you can't because these are all unknowns and you can't just get rid of them. You literally have to solve them at the same time in order to do it. I don't know, does that make sense? That's what it looked like you were doing. You were creating something like W1 equals W11 plus W12 plus W13 plus W14. And W2 is 21, 22, 23, 24, so forth. And then you were taking that and dividing it by its right-hand side. But that doesn't work. You can't get rid of these. They're unknown and they're all different. You can't eliminate them in the process. So if you got rid of that whole chunk of code, or 75C or something or other, get rid of all of that. You already computed the W's, you computed the right-hand sides. All you really need to do is add that line, and you're good to go. I guess, and add in the port side of the wing.
yeah, like the theory I understand, just the coding itself, it's kind of like I think I did something wrong in the code, which yeah, now I realize that.
Yeah. This is the linear algebra piece, and I know we talked about it a little bit. I guess I didn't quite explain it well enough for you to get it. This is a longhand approach, but it's not the solution approach. The solution is to leave it in the matrix form and let MATLAB do all the work for you.
Okay. And how I get the port side?
So the equation is the same, except that let me see, I can bring it up here. They actually work one of them for you. I have it open already. Let's see. Do not find it real quick. Right. So he actually solves for a few of them. Here's the port of 1, 1. what changes, we go way back up to this equation. It'll be this equation. But all of the X1s and Y1s and X2s and Y2s, they'll be the port side instead of the starboard side. So the X's are the same, but the port gets a minus sign.
So anything with Y, it's
Well,
you're just gonna change.
not the M's. The M stays.
Yeah, the end. The ends.
Yeah, the ends get an opposite sign. Yeah. So what you can do is you can just take the vector you created for Y2, Y1N and Y2N, and then you can just create a port side by saying it's the negative. Yeah, that's pretty much it. And then I think you'll want to check against the one example he does here. This one, I think there's a missing sign out front because all of these, all the delta y's in that equation, all these things like y2n minus y1n, there's two negatives involved there. So there's going to be all these sign changes. I think all of the terms end up getting negative. So you can compute it the same way. And then when you sum them up, yeah, here you go. You can either take care of the minuses by having a slightly different equation, or you can just add a minus sign here, and that takes care of it. But when you first start to calculate them, check it against the one they give you. 11P. So see if you get the 18515. If you don't, change. If you're getting the wrong sign, then just throw the sign change in there.
I'll try to work on the code again and see if I can get it right. Yeah, because I'm kind of interested in this problem, this exact homework. I want to get it right. Like it doesn't really matter if I get it right anymore.
It's kind of a cool code when you get it working.
Yeah. Do you mind if I when I finish it, can I just send it to you or ask you more questions about this?
Yeah, sure. Absolutely.
Okay. Thank you.
Yeah, no problem.
That's the port side.
The alternative, if you don't want to worry about that port side, is that you can literally define the geometry for both sides. So we were only defining the geometry for one side. Here's the symmetry plane, and we had the wing out here. I don't know if that's showing up. Markers are basically dead. And so we did like the four panels here, the 4 control points. But if you go ahead and you define the whole geometry, and you, instead of a 4x4 system, it'd be an 8x8 system. Then you can use the same code that loads the influence coefficients from tip to tip, and then you don't worry about the port side at all. You're actually handling the whole thing. If you skip the port side, what the code actually does is it treats this as a wingtip, and this is a wingtip. So if you had an unswept case, it actually looks like a full wing, just cut off to one side. If it's swept, then it's kind of a weird solution. It tends to put more lift out at the wingtip, but this is that wingtip, but this is also a wingtip here. So you get a solution, it's just not the right solution, or it's not the geometry you think it is.
Okay, and for the actual lines when you do it on the graph, there's like some kind of an auto code to do the line as long as they change, or I have to do this manually?
What do you mean?
like the black lines and the red lines.
Oh, you mean to plot it?
Yeah,
Uh, yeah, I don't think there's any, I mean, like for the exterior, I think I just literally, I know the 4 corner points. I think I just I create a vector of length 5 for the X and the Y coordinates to load up that. And
Yeah.
then these you technically kind of
because
know.
for every case I had to do this.
Yeah. I mean, it ends up all being, you do probably a for loop for drawing each panel, or you grab all the X1s, Y1s, X2, Y2s. I don't think, yeah, there's no super automatic way. You have to write the code for it, but you technically have all those coordinates, or you can compute all those coordinates.
Okay. Okay, I'll try to fix the code and add the equations for the port side and try to run it again, see if I could get the exact same number. But I'm gonna have to work on homework 6 first
Okay.
because it's due
What
soon.
what I'd recommend is definitely step by step, go through your code and you can break, if you call these things different terms in here, there's like 5 different terms. And if you call them different terms, then you can actually compare them bit by bit at these various stages. And so, you know, if you're not getting these numbers, you need to go back and check your math in here and make sure you're actually doing it right. If that's all working.
I think I got the starboard side right. I got
Okay,
the starboard side right. The only thing I did not count for is the port side.
yeah, okay. Good. Yeah, if you, and then you should be able to get these things exactly. If you're missing the port side, you won't, but if you add in the port side, you should be able to get the gammas exactly.
Okay. Yeah, I'll first thing is I have to add the port side and fix the code because I think I made a mistake by combining all the W's at one.
Yeah,
My initial thought is that to get them in matrix, but for somehow I just combine them as a sum, which is
Yeah.
just not really
Yeah.
works.
yeah, you had the matrix, so it was there.
Okay. Thank you, Professor.
Yeah, but
Have a nice day.
okay, we'll see you later.